Okay, so let's review a little bit what we did last time. Okay, we are talking about NLP. We talked about some simple models that really were used quite a lot, and to a lot of, even though this representation loses a lot of information, but this is how a lot of the systems were built, prior to definitely 2010, if not 2015. So bag of words model, doing things like TF-IDF, using SVMs and logistic regression for classification tasks, um, and then starting to use neural networks. One simple way is to use bag of words with the fully connected networks, uh, uh, but that doesn't work so well. So something that takes sequence into account, and that's where we introduce RNNs. Last time, right? And we saw, the RNNs, the way it proceeds is it basically maintains a hidden state at time t, which is, you can think of the position of uh, position information of the word in the sentence as t. And given the word at this position, U, that goes through kind of a word embedding matrix. So you get the word embedding over here. And then you have the previous state, you have a transition matrix, and the evolution of the states is given by this, where F is some nonlinear function. Okay? And at every step, you have the choice of having an output. So, and that is given by kind of, you basically are taking the ST over here, the state, and applying the matrix P to get OT, right? So, and then you can optimize it over the data, over the sequence, and then the loss will be the average loss over all the sequences. And like we talked in last time's lecture, or not last time, the time before, that you can use variants of STD like Atom to optimize this network and try to figure out the parameters, right, which are U, W, and V. Okay. And then we looked in particular at, for example, text classification. You can look at the final state, right, as the output probability, as giving the output probability. You can have multi-layer RNNs. We also told you that RNNs actually don't really work, but you can replace them with something called LSTMs. They're much more stable. RNNs, one of the reasons why they don't work is because they have, they're hard to capture long-term dependencies. There's a vanishing gradient problem that happens. And so as RNNs really cannot be trained quite well, but LSTMs can, right? And so a lot of then the systems that came up, I want to say between 2012, 13, 14 or so, till 2017 or 18, right, were based on LSTMs. For example, for translation, right? Translation from one language to another language, for example, from German to English. And most of the methods used this kind of encoder decoder architecture, where the encoder would produce like a final hidden state, and then the decoder will use this and kind of the word that is produced, that it produces at the previous step, and this final state to do translation, right? And it actually worked quite well in terms of that it really like led to a big increase in the quality of machine translation, at that time. And then, of course, there were several. So this is kind of an illustration of and LSTM. Of course, they had multiple layers. I think some of the commercial ones use like 24 layers of LSTMs. But then actually a really neat concept came about, and the concept came about before the transformer paper, right? So the transformer paper is something that many of you have probably heard about or read, and it's the title of the transformer paper, very catchy title, right? Which is attention is all you need. So attention was actually, in some sense, invented before the transformer paper. And the idea of the attention is actually, quite easily explained even in LSTMs. And that's where actually the first attention work was done. So over here, like if you look at this illustration, right, if you see a particular sentence, let's say in German, then you have these hidden states, H1, H2, H3, but you only end up using H3, right, the final hidden state, in actually doing the translation, doing the decoding, okay? But, we know, for example, especially in translation, right, that there are going to be words in the target language or the target sentence that will actually correspond to words in the original language sentence, right? So, so instead of just using the hidden state, the final hidden state, you might actually want to use some of these intermediate hidden states, right? So that's really what kind of attention does, okay? So let U be the current decoder latent state. Okay, so the decoder is working, and let kind of V1 through Vn, suppose there are n input words, let them be the latent states for each of the input words. Okay, then what you can do is you can actually take an inner product between the current decoder latent state and each of the latent states for each of the words. Okay, so you can think of this as paying attention to the first word. U transpose V2 would be attention to the second word, and so on. And then U transpose Vn will be the attention to the nth word in the sequence. Okay. Now you want to convert them to a probability distribution, convert this vector to a probability distribution. Remember that this vector is of size n. And then what you can do is you can take a softmax. And so you will get a probability vector. This probability vector will be non-negative in each of its components, and the values will sum to 1. That's why it's a probability vector, okay? And this is like the attention, and then the way you kind of compute the context vector, right, will be, so that's the, given the current word vector or latent state, U, the context now is you can think of it as a linear combination of all the attention, of all the latent states of the input words. Okay, so in particular, it is P1, V1 plus P2, V2 plus Pn, Vn. So it's not only a linear combination, but it's a convex combination, which means that it is non-negative and it actually sums up to 1. Okay, and that can be more compactly represented by V times P. So just think about it, right? So suppose that the current latent state has a very high inner product with the first input word, with the latent state of the first word. That means that P1, and if you do the softmax, if this is much larger than the other, remember that softmax is actually an exponential function. It'll amplify this kind of difference. So this will become a very peaky distribution, and this would be almost 1. In which case, this context vector is actually just the almost like equal to V1. Okay, so that's kind of the idea of attention, and the way you can actually use it in LSTMs is now contrast this picture where you are only using the last state to do the translation, with this picture over here, where you're using basically each of the states of the encoder, right? And this, is just a representation of what I just said, right? You basically take the inner product of the current latent state with this encoder state, then you do like you get a score, you do a softmax, and then you do kind of this addition. So it's basically just capturing what we just said over here. Okay, and that's what you feed into the next state. So this is the decoder hidden state. It is getting, so this is the decoder hidden state. This is representing the inner product with the encoder hidden state, and so on. Okay. So now, and then of course, the drawbacks of LSTM still do not kind of go away, right? Some of the drawbacks is that the computation is inherently sequential. And one of the big things that the transformer did was that it actually made the computations naturally very parallel. And that's very important because of that, you can then start using the hardware much more effectively, right? So for example, you can use your GPUs quite effectively, right? GPUs thrive on that, okay? So let's talk a little bit about the transformer. So the transformer, as the name suggests, the name of the paper is Attention, All You Need. It was published in 2017, and it is an architecture that relies entirely on attention. Okay, it does not use RNNs. We haven't talked about convolutional neural networks, but doesn't use that either. Okay, and one of the big reasons I think that this has been successful is because it can actually reuse the hardware, underlying hardware quite well. Okay, so here is the uh, the uh, kind of intuition or the way the transformer works at a very high level. So suppose you have a sentence. So this is again an example for machine translation. Suppose you have a sentence in French and you want to translate it into English. Okay. So what you could do is there'll be a transformer encoder, and you can have multiple layers of transformer encoder. And what the transformer does, well, as the name suggests, it does transform. It transforms. So it transforms. So what will happen is that there will be 3 vectors associated with each of these words. And then each of the layers will actually transform each of these 3 vectors into 3 new vectors. And it'll keep on doing that. Okay. And it'll do it by using the attention mechanism. And this is called self-attention. So it'll actually use the relationship between the words in the sentence. So it'll actually look at over here, right? Because if you think about over here, I'm a student, then there's a relationship between I and a student. That attention mechanism will kind of pick up for that pair of words. Okay, so if you look now, over here, there are, like I said, there are several layers of encoders, several layers of decoders. What's inside each encoder and what's inside each decoder. And of course, we'll go into further detail into the self-attention and the feed-forward network. So the self-attention is the main architecture used in the transformer. We'll look at that. Again, it will be a little bit similar to what we saw when we were looking at attention from the decoder to the encoder, but this is self-attention. So this is attention within the words of the input sentence or within the tokens of the input sentence. So there'll be a self-attention layer, and then there's a feed-forward layer, right? And on the decoder side, you have self-attention at the bottom, feed-forward at the top. But in between, you also need attention between the encoder and the decoder, right? So for example, correspondence. So this should be correspondence between, so suppose you're doing machine translation. This is self-attention, attention between the words or tokens in the input sentence. Self-attention, if you have generated some number of words already, right, in the output, in the target language, then this will be self-attention between those words. And then you need to have the attention that we talked about before, which is attention between the encoder and decoder. So that's kind of the encoder-decoder architecture. What has happened subsequently is that, even though today we will talk about encoder-decoder, and that's what is actually used, that's not actually used, though that's not the architecture that's being used to generate the current best models. It turns out that they just use a decoder-only model. And we can come to that a little bit, but from historical significance, that's how kind of the transformer architecture came about, and most of the initial LLMs were trained using this encoder-decoder architecture. So let's now look at any questions so far. Okay, so let's look at the encoder architecture just by itself. Okay, so each word will go have a corresponding latent vector. Remember that even in LSTMs, right, we have a word embedding matrix for each word. Similarly, at the bottom layer, there will be a word embedding for each token or word. Okay, and that'll be the input embedding, and then it'll keep on being transformed from one vector to another. And more precisely, each layer of the encoder will do the following. It'll receive like a list of vectors as input. So if you're thinking about machine translation, right, the input sentence is there, and it'll basically receive, when I say a list of vectors, it is a vector for each of the words in the input sentence, right? So if the sentence is of size, let's say 10, then it will receive a list of 10 vectors. Okay. Then, like we said over here, there's going to be a self-attention and a feed-forward. So the self-attention layer will, you'll pass these vectors through a self-attention layer. Then you will pass them through into a feed-forward layer. And the output of each layer of the encoder will again be a list of vectors. So in the example I said, let's say there are 10 words in the sentence, input sentence, then it'll be a list of 10 vectors, and a transformer will transform them into, take input as a list of 10 vectors and will output a list of 10 vectors. Okay. So over here, you can, I think we'll carry this example a little bit later. So, suppose you have thinking machines, right? Just two words in the sentence, right? So you have a list of two vectors. You transform them into through the self-attention layer, and then you pass them through a feed-forward layer, and then that becomes the input to encoder number 2. Okay, so now let's see how kind of the self-attention works. And again, the main idea in self-attention is, that the actual meaning of each word may be related to other words in the sentence. So in particular, the whole idea is that, if you're computing the latent vector for each word, you would compute it as a weighted combination, which is computed through the attention mechanism of other latent words in the sentence. In the earlier case, we had seen you're looking at, the context of trying to compute, in the context of encoder decoder. This is self-attention. So suppose you have this sentence, right? The animal didn't cross the street because it was too tired. Note that, these kind of try to represent the tokens that are used, and the tokens don't have a one-to-one correspondence with the words, right? So this represents the different tokens: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So now you have a list of 14 vectors. In the first layer, right? You would basically, this would pass through word embedding layer, right? And then would get translated into a vector, let's say of dimension, 512, right? And in layer 5, there would be like a 512 dimensional vector for each of these tokens. Okay, so there'll be, I think we said there were 14 tokens over here. So this will be a list of 14 512 dimensional vectors. And then it'll get transformed, okay, by layer 15 from the input set to the output set. And in between the first thing that will happen will be an attention, okay? And if you look at the attention layer, right, the motivation is, so if you look at this sentence, the animal didn't cross the street because it was too tired. The question is, what does it refer to, right? I mean, forgetting about, like it could potentially refer to because, it could refer to street, it could refer to it could refer to cross, and so on, right? I mean, we know English, most probably it refers to animal, right? Now, there could be some cases where, especially when you see like jokes and so on, right? It actually refers to some other kind of noun, right? It could potentially refer to the street, right? The animal didn't cross the street because the street was too tired, right? Of course, that's not the meaning over here, but you can actually have jokes or so on where, the meaning is, the standard usage of it might not be what is meant in the sentence, right? But over here, you will see, like, if you compute the attention score, right, the strength of this line is supposed to, I guess, signify, the relationship, right? That it probably refers to the animal. It is probably also the one that is too tired. And if you, for example, look at the word street, then street will finally not get too much attention on tired. Okay? And of course, that'll be an output of that'll be a result of how the attention mechanism is trained. Okay, so now let's look into more deeply into the self-attention layers. Okay, so remember that I said that there's a list of input vectors, right? So over here, we are assuming there are n input vectors. Okay, and then the self-attention parameters are actually going to be 3 matrices: WQ, Q for query, WK, K for key, and WV, V for value. Okay, so basically you have these matrices, which are these weights for query, key, and value. And the way they will work is the following. For each word I, right, so you have xi over here. So you have the vector xi. I'm going to compute the query vector, and that is xi times wq. Okay, WQ actually in general actually will not be a square matrix. Okay, so for example, over here, below you can see this thinking machines, and you can see I think you can see my cursor, right? So this purple matrix WQ is 1, 2, 3, 4 by 3. It's a 4 by 3. It's a rectangular matrix because it is transforming a 4-dimensional vector to a 3-dimensional vector. So the dimensionality of xi and qi can be different, and typically is different. Okay, so the query vector is qi is equal to xi times wq. Similarly, you compute a key vector, ki is equal to wxi times wk, right? And you basically want to match up the query vectors with the key vectors. It's actually giving you one level of additional indirection, right? So you could have done WQ here and WQ here also, but this gives it more flexibility. The WQ is actually different than WK. Okay. And then there's also something called the value vector that is xi times wv. Okay, so this is how. So on the bottom, we have this input thinking machines, 2 tokens for simplicity. You can see xi, x1, and x2. Each one of them is a 4-dimensional vector. WQ is a 4 by 3 matrix. So you can take x1 times WQ, that gives you Q1. You have x2 times WQ, and that gives you Q2. That's now the query vector. Okay, corresponding to each of the input tokens. So now you've computed 2 query vectors. Similarly, x1, 4-dimensional vector, times wk, k being a 4 by 3 matrix. You get k1, which is a 3-dimensional vector. And similarly for machines, you'll get x2 times wk, and that will be k2. Similarly with value. So now, given this token x1, you actually computed 3 things from it. Query vector, a key vector, and a value vector. And now is where self-attention comes in. So for each word, you compute the scores to determine how much focus to place on other words. So in particular, the attention score for word J to word I is Qi transpose Kj. Okay, so just think about it. So we computed the query vector Qi for word I, key vector for word J, and the attention score is Qi transpose Kj, right? So remember this example that we are kind of carrying through, right? So you have x1, and that leads to q1, k1, v1, depending upon the 3 matrices, wq, wk, and wv. Similarly, from x2, you'll get q2, k2, v2, right? And again, x2 times wq is q2, x2 times wk is k2, x2 times wv is v2. Okay. Now, given that, you're going to compute the attention score. So let's look at the attention score for word 1 to word 1 to word 1. So that's actually just Q1 transpose K1. And suppose it is, let's say, 112. Okay. And now you have to compute also the attention score for word 2 to word 1. So it's going to be Q1 transpose K2. And that's what's done over here. Q1 inner product with K2. And suppose that is 96. Okay, so now you have basically 2 scores because you have 2 tokens. And what you then do is you take a softmax. Okay, and there's a little bit of normalization that takes place, right? So you can actually divide by, some factor which depends upon the dimensionality, right? So in this example over here, 112 divided by 8 gives 14, 96 divided by 8 gives 12. And when you take the softmax of this vector 14 and 12, it gives you a much peakier distribution, right? 0.88 to 0.12, whereas 14 and 12 were not that different, right? But because it's an exponential function, then the softmax can actually be quite different, okay? Then what you do is once you've computed SIs, which are the softmax values, so these SIs essentially correspond to these numbers, 0.88 and 0.12, since we are only taking the example where n equals 2, okay? Now what you do is you multiply this softmax value with the value vector. So remember, this is the value vector v1. So what you would do is you would take, and this is the value vector v2. So what you would say is that the way that you transform the vector is by taking 0.88, multiplying it by v1. So that's over here. 0.12, multiplying it by v2. That's given here. And the reason this is in a much lighter shade is because 0.12 is much smaller than 0.88. Okay, so you're actually not taking that much component of v2. So you have v1 and v2, and then you sum it up. Okay, and that gives you z1. So just a quick check. Suppose I have, and similarly, then you do for z2. Z2 will look at the attention scores again with, so it'll be Q2 times K2, Q2 times K1, and then you would again compute the attention, the self-attention, and this addition of the value vectors. So quick check. Here I've shown only two words, right? If I have n tokens, right? So like over here, how much computation is required to compute this attention? For the ith word, you actually need to go through the keys of all the word tokens, all the other tokens, and the token itself. Okay, so you actually get n terms in this summation for each word. There are n total tokens. So this computation is actually order n squared. So quite a lot of work. Okay. Bad because it scales quadratically, but can actually also be good because it means that there are lots of matrix multiplications, and modern hardware like GPUs is actually very good at handling matrix multiplications. Okay. So, we kind of explain this over here, right? In a machine, the way it would be done is, here we kind of are looking at thinking machines as separate. Typically, what you would do is you would stack these. So this first row would correspond to thinking, and the second row would correspond to machines, right? So you would do this query vector for both the tokens. If there are n tokens, there will be n rows in this query vector. Okay. Similarly, you'll have not just a single key vector, but you'll have a key vector corresponding to each of the tokens, right? So and then similarly for the value, it's no longer a value vector, but it's a value matrix, except that each row corresponds to a different token. And then you can, do a softmax operation, which is defined over each row of QK transpose, right, and multiplied by V. So you can actually represent this computation quite efficiently, quite compactly, right? So Q is equal to X times WQ, where the number of rows of Q is the same as the number of rows in X, which is the number of tokens. Okay, so you compute the Q matrix, you compute the K matrix, you compute the V matrix, and then you do the softmax operation, right, over each row, and then you get a matrix. Softmax QK transpose is a matrix, which is what's sometimes called a stochastic matrix, where each row, all the entries are non-negative, and it sums to 1. Okay, so you end up taking a convex combination of all the value vectors, and that's how the transformation is done. Okay, so one thing you will notice is that the transformer is not complete right now, right? It has, in this example, taken a 4-dimensional vector and transformed it into a 3-dimensional vector. But what we want is that the 4-dimensional vector should be transformed into a 4-dimensional vector, and we'll see how that happens. Any questions so far? So this is pretty important. The attention mechanism is really kind of neat and is at the heart of the transformer. Any questions? Okay. So then instead of using just one single, set of WQ, WK, WV matrices, you actually can use many of them. And this is what's called multi-headed attention. Okay, so in attention head number 0, you do what I said, and then you similarly have, so those ones, you call those matrices Q0, K0, and V0. And then for attention head number 1, you call them Q1, K1, and V1. Okay. And so the output of attention head number 0 is going to be something like Z0, right? Like over here, except you put a subscript on it. And similarly for attention head 1, which corresponds to these different matrices, you have Z1. And typically you'll have, let's say, 8 attention heads, in which case you will have Z0, Z1 through Z7. Okay, so what's happened so far? Thinking machines, these tokens, each were represented by a 4-dimensional vector. And right now they are being represented by, if I just concatenate all of them, I'll have 3 times 8. It's a 24-dimensional vector. Okay, but remember that we want 4 dimensions. Okay, so typically what you would have is you gather all these outputs, Z1 through ZK, you multiply by a weight matrix to reshape to get basically 4 dimensions, and then you pass on to the fully connected layer. Okay, so in particular, you concatenate all the attention heads. So in this case, it gives you, remember there were 2 tokens, right? And 3 was the output dimensionality of each attention head, right? So you get a 2 by 3 matrix for each of the 8 attention heads. And if you combine them, it is a 2 by 24-dimensional matrix. Then you can basically multiply it by a 24 by 4-dimensional matrix. Okay, so this 24, the number of rows in WO, match the number of columns over here. And this 4 is because the input dimensionality was 4. So you're mapping it back to 4 dimensions. Okay, so once you do this times this, the result is this Z matrix that captures the information from all the attention heads, and we basically send this forward to the feed-forward network. Okay, so this is the overall self-attention part of the architecture. Thinking machines is our input sentence. We embed each word, in this case, as 4 dimensions. You have these 8, if you have 8 heads, you have 8 kind of matrices. Sorry, 3 matrices for each head. So there's W0Q, W1Q, W7Q. So there are 8 query matrices, 8 key matrices, 8 value matrices. Okay, you multiply X, which is the input tokens, with these weight matrices. You calculate the attention using these QKV matrices. You concatenate the result for each head is given here. You multiply it by this weight matrix, and you get out Z. And then, of course, like in all the encoders, so this is, what I was talking really about the first layer when we say something about embed each word. But all the encoders other than the first layer or the 0th layer, we don't need embedding, and you would basically look at the output of the encoder right below and use that as the input. So this, if R is the output of the previous encoder, you would use that as the input over here. So that's why it says split into 8 heads, we multiply X or R with these matrices. Okay, questions so far?
A couple questions, mate.
Yeah.
So these heads, like structurally, are exactly the same. So I suppose when we train these, we try to like initialize them differently to break the symmetry, right? This is basically what during the back propagation, like these attention heads attend to like different parts of the inputs. Just
That's what it. Yeah. Go ahead. Let me finish your question.
Yeah, I said these heads are attend to like different part of the inputs just organically by like the random initialization and then go through the back propagation. Am I right? Or is there something?
As far as I know, nothing special is done to make sure that these are, somewhat different. And that kind of just seems to happen by itself. And I'm guessing, as I have hypothesized that it is due to the different initializations maybe that is done.
And is there any
Then
like
Nilesh, feel free to chime in, if you think otherwise. Yeah, go ahead, Hamid.
yeah, the next question was that is there any insight behind the key query value? Like, why don't we just have you mentioned that this extra like query and key make it more like flexible, but
Yeah,
can we like add another thing like query key code and value or something, to make it even more flexible? Or
yeah. So look, the attention paper I said was published in 2017. When you first look at the architecture, you always have these questions, right? So many people have tried to, for example, change the order n squared computation in the attention mechanism by something which is, looks on paper to be more efficient. They've also, I think, there have been lots and lots of modifications to the transformer architecture. So far, the transformer architecture has actually proven to be quite resilient, right? And so, there's also this thing that is happening right now where you have these models are being produced um, using the transformer architecture. I don't think anybody um, um, there's any controversy about whether GPT-4 or Gemini 2.5 Pro, the latest models, are transformer architectures or not. They're transformer architectures, but some details might be different, right? So there may be some weight sharing going on sometimes. So those details are sometimes not obvious, based upon the input and output of the model. Then, of course, there are the open weight models that Google has, for example, Gemma, that Meta has in terms of Llama. DeepSeek, I believe, also is an open weight model. So there, of course, you can figure out exactly what they are doing, and what they are doing in the sense of what the model actually looks like. Did that, I mean, I guess your question was like, oh, like how can you even, like, for example, so you can try to do ablations, right? Which is, you can try to do experiments and say, oh, look, I'll make K0 equal to Q0, K1 equal to Q1, and so on, right? And then see what the results are, if there is an evaluation set. And, there are, thousands of these evaluations done. Sometimes the tricky part is that, if you do evaluation at one scale in terms of how much data you use to train, what is the dimensionalities of this, the conclusion might not hold at a larger scale when the model becomes bigger. So in general, like, there is multi-headed attention. I think there is one other paper that has something called multi-query attention, and that's also very widely used in the methods. So I think, for example, Llama paper says that they use multi-query attention, and sometimes the reason for doing it is, expressibility. Sometimes the reason for doing this is better utilization of hardware and things like memory cache and so on.
I see. Thank you.
Yeah. So, I mean, like, I think I was at a conference which was like, oh, 5 years from now, will the attention architecture remain the same or will it change? And I mean, I think honestly, nobody knows. But, looking back at hindsight, it's actually proved pretty resilient over the last 8 years.
And how they handle like the different sequence length, like in the LSTM based translation, for example, we could see how like a, forward, for example, German thing can translate
Yeah.
into English, but
So,
how it
so typically they have like a beginning of sentence token and an end of sentence token, right? And then you can basically pack more things into the sequence length.
I see. So
you could, like, okay. And then of course the latest decoder models are, so the latest models are essentially decoder only. And what they are doing is basically doing, predicting the next word.
right.
Right, so they are these causal kind of models, right? They are predicting the next words in the sequence. So they do it for word 2, word 3, or token 2, token 3, token 4 in the sentence. So you basically give a long sentence, and then you pass them through the transformer architecture. You do forward pass, you do backward pass, you change the weights, then you go on to the next sequence and so on.
I see.
And then, of course, there are so many different tricks that are used in terms of trying to, optimize both the hardware and, there are some things maybe about, what kind of data do you send as inputs? Does it matter what sequence it is in? Does it matter whether it is repeated or not? So there are lots of different things people have played around with, and some people have different recipes for doing it. Yeah.
I see. Thank you.
Okay. Let's see. So that's about the self-attention, right? One of the things that we actually haven't talked about is we sort of said something about bag of words model. Then when we said something about MLPs, we said, well, you can use a deep neural network, but if you use MLP, that's still kind of still using bag of words, because how are you capturing the sequence information? And so far, we actually haven't seen. We've said this is a list of vectors, right? So if I permuted these vectors, so far, there's not that much different, right? So typically what happens is that you do a positional encoding. So not only do you have an embedding of each word, but you have an embedding of the position. So what we've talked about till now, it ignores the sequential information. What then you can do is you can add positional encoding vector to each xi being the embedding of the input word I, okay? And the position encoding depends only upon the position I. Okay, so typically and then you get, the actual x1, the embedding. So you have one is the embedding without the position signal, and then the embedding with the time or position signal is basically you add this position embedding vector for each position. Okay, so this will be like the word is the first word in the sentence. This is the embedding for the second word in the sentence, and this is the embedding for the third word in the sentence. The positional encoding is an important part of the transform. And then the way they do it is you can have different ways of doing the position encoding or even learning the position encoding. Sometimes you can have parameter-free versions where you have like a sine or a cosine function with different wavelengths. That's what was used in the original transformer paper. Or you can try to actually learn a position latent vector for each position. The characteristics are that this would be smooth versus non-smooth versus sine and cosine, which will vary smoothly with position. But this is kind of parameter free, whereas this is kind of data driven and learnable. Okay, and then there are other more sophisticated methods that people can use to do the position limit. Okay, so questions? Questions so far on the transformer architecture?
Sorry, about the positional encoding, is that like if, for example, our embeddings is like dimension of 512, like
Yes.
positional encodings also have the 512, so
Yeah.
for each position, right? So like
Yeah.
for first position, we have like a 512 dimension vector, and then for position,
Yes.
we have another 512 position vector, and then we just
Yes.
do the, okay, thank you.
Yeah. Yeah. So that's how it is done right now. Uh, and then, you probably heard about like, the sequence lengths getting bigger and bigger, or context lengths getting bigger and bigger. And there are other tricks people use to handle
Are we
like larger
supposed to be
context
able to
lengths.
see the slides?
Oh, sorry. Did you want me to share the slides again, or?
Just yeah. I think there's something I meant. Yeah, I think it'll help. I think. So I just wasn't sure if you meant to be screen share or not. I just wasn't making sure.
Oh, no, I actually stopped screen sharing because I was going to move on to the next, we have about 10, 15 minutes. I was going to share a different set of slides.
Okay, my bad.
Okay, any kind of questions so far, or?
I have a quick question.
Yeah,
This might be I didn't quite understand so why is there a distinction made between key query and value matrices when like aren't they all receiving like the same input for like self-attention, like so why, like what is the distinction between them? It feels like they're all kind of receiving like the same input and like they're just like three different matrices, right?
sorry, what do you mean by that? So remember that the you have these input vectors, and they get transformed. Each of them gets transformed into query and key components, key vectors.
Mm-hmm.
And then when you compute attention, you actually look at the dot inner product between the query, a vector of one token, with the key vector of the other token.
Oh,
It's
okay.
not like you're looking at the self-attention as I mean, somebody could have designed it, and maybe they did try it when they were thinking of the transformer paper. They could have said, okay, I'll take each token or each vector, I will transform it into a query vector, and then I'll take an inner product between all the query vectors. That could
So
potentially have been the definition of self-attention. But I'm guessing that people found that this is much more expressive because you have more parameters and works better.
so wait, can you give when would an example be of like when like the key and the query and the values would be like different, completely different? Like when would like a good example of that, like a real world use case for that be?
Oh, I mean, I'm guessing that, for example, again, Nilesh, feel free to chime in. Like if you look at, maybe we can actually do that, right, as part of, well, I don't want to give you more work, but you can look at, for example, the weights in, let's say, the llama or gemma, right? And you can look at the different WQ vectors and WK vectors. And remember that these have, these are the weights after the pre-training. And
No, I
my
don't mean like the
impression
weights.
is
I
that
mean
they have,
like
oh,
I mean like the
oh,
input, the input themselves, like you said, like self like attention is more general than self-attention, right? So one would like a good use case of like the input to a key and the input to a query and like the input to a value be different. Not the weights.
oh, the input, you mean like the XIs?
Yeah.
Okay. So you're saying that, okay, so you're saying that for self-attention, XI is the same, right? But for example, when you're doing cross-attention in the, uh, 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 when you're, for example, doing encoder-decoder cross-attention, then they will be different, right? Because you are looking, for example, if you're looking at machine translation, right? You might be
Mhm.
looking at the word in the target language in English and looking at the cross attention, which is the attention with the corresponding words in English. So French on one side and English on the other side.
All right, that makes sense. All right, thank you.
So in that case, it's not just it's not self-attention in particular. Does that make sense?
Yeah, that makes sense. Thank you.
Okay.
Yeah, just to add on top of that, usually like for the key and value, like you tend to have the same input, xi, but for the query, like as Professor said, like when you want to contextualize your thing that you are looking at the query that you want to process, if that is different, then the input to that can be different. So, for
Yeah.
example, here in the case of translation, if you are generating like French tokens, so you want the French tokens to look at the English tokens. So there you'll
Right.
have a
So I
different.
think what right. So what I think what Nilesh is saying that in this case, this particular X could actually be different than this particular X when you would do cross attention. So
All right.
this would be X1, let's say in the target language, and this would be X2, which is in the source language.
All right.
Right.
Okay, and typically this will be the same. The X in this will not be different.
All right. I see. I got it. Okay, thank you.
Okay, let's see. Okay, and like this is like the main application I think they were trying in the transformer paper was again neural machine translation, right? So they had two sizes of transformer models, one which was base model, which was smaller, transformer big, which was bigger, and then they saw that this gave them much better results than previous architectures, some of which were based on convolution networks, some of which were based upon other kinds of attention, but not have the transformer architectures. Okay, and these are some blue scores, and of course these numbers are 2017, kind of much older. And the way the transformer architecture was proposed was an encoder decoder architecture, And now people use just the decoder on the architecture. Okay, any other questions? Okay, so I think transformer architecture is really the one that is really used a lot, just for historical purposes. As things evolved in NLP, there are just a few things that you might want to know about, but in some sense they are ancient in some sense right now. We'll put them in the slides and you can go through it, and I can go through it really quickly. But there are various ways of kind of embedding words, and earlier people would, for example, the vector space model, people would just use a static representation. But some of the things that happened, around 2012 and so on, are that you started looking at the context of the word, right? So you would look at a particular word, you look at the words before it, you look at the words after it, and you would codify this word using this word context pairs. So in particular, for example, if you have a sentence like, the quick brown fox jumps over the lazy dog, then you might use training samples, which are, centered on that particular word under consideration, and then the context. So for example, here, brown, brown the, brown quick, brown fox, brown jumps, and so on, right? And so this led to a couple of things. Well, like one of the ways of embedding vectors, again, I'm not going to go into details over here, but there was, kind of a seminal paper called Word2Vec, which basically was able to take Word and get, it's called, an embedding. Again, like I said, this has been surpassed now. The embeddings which are provided by, Google and OpenAI and so on are much better and don't use Word2Vec. But one of the interesting things is that you can kind of use these earlier techniques were used to produce embeddings of words. And then one of the interesting things that people found out is that there was some really interesting relationships, right? So for example, if you did once you got these vectors, you saw it. They found that king minus queen was equal to man minus woman. So that kind of captures male, female. If you looked at different verb tenses, then swam minus swimming was the same as walked minus walking, right? So the past tense versus kind of the present tense. And then even with things like, Russia minus Moscow will be equal to Japan minus Tokyo. So even though these representations can sometimes look a little arbitrary, there was a lot of semantic information that was being preserved. And a lot of it was because, the way of producing these lower dimensional embeddings was really scaled up, right? So they ended up using tons and tons of data, which had not been done before, and they were able to harness the systems and the powers of the GPU and the TPU to give, these meaningful results. So this is not used right now, but, Word2Vec in 2013, like, is an example of, the early days that has important kind of historical context. Okay, so we'll include that in the slides that we upload. So I think that's it for today's lecture. Any questions?